Hi, I am Avirup Ghosh, a PhD student at the University of Edinburgh. This video is about my PhD research. The topic is analysis and privacy preserving algorithms for spatiotemporal sensing. Currently, I am looking for a research position. If you are interested in hiring me or you know somebody who can be interested, please feel free to contact. Across many applications in the real world like urban analytics, sensors are in general spatially distributed and they collect data over time. In my PhD, I mainly focus on analyzing such spatiotemporal signals, especially concerning mobility, time series, complex networks, etc. I propose theoretically sound and practically useful methods inspired by geometry, topology, and statistics. Prior to PhD, I was a software engineer at Intel Corporation, working on Bluetooth technology for Android devices. Before that, I obtained my master's in computer science from IIT Bombay in compiler optimization. Now let us go over three main contributions of my PhD research. Let us first talk about periodic pattern analysis in temporal noisy streams, published in CIKM 17. These are footstep events collected from a smartphone device. We want to detect periodicity in such event streams. This is challenging because periodicity and phase changes over time, like these events here, and it contains false positive events. These characteristics are common in many applications, like surges in traffic, daily habits, heartbeats, etc. We propose a particle filter-based periodicity detection algorithm based on novel probabilistic modeling of such events. We first guess k periods and then we refine our guesses based on each event arrival by calculating their likelihood values. We find the period as the median of the guesses. This method uses constant and low number of particles, therefore it is time and space efficient. It is more accurate and efficient than existing techniques like Fourier transform, autocorrelation, etc. It operates in online fashion. Next, let us talk about our work on spatial trajectory analysis using topological constructions, published in 6 Spatial 18. Here we predict motion at large scale. Suppose a user comes along this way and we want to predict his direction at scale r, say 500 meters. Here we propose topological signatures, which are fixed dimensional Euclidean vectors. Like the trajectories here are represented as single points in this signature space. The dimensions in this space correspond to obstacles in the domain. These signatures preserve homotopy types of the paths. Signature-based learning methods can predict motion better than even neural network-based models on raw location data. These signatures enable standard Euclidean analytic tools like clustering, nearest neighbor search using locality-sensitive hashing, dimension reduction, regression, density estimates, etc. These signatures can be computed efficiently using online and distributed computing. To construct the signatures, we assume mobility on the edges of a planar graph. We construct directed edge weights called differential forms, like these arrows and the values here. The signatures are integrations of these differential forms, like this green trajectory here has signature -2. Next, we discuss privacy concerns for spatiotemporal data analysis. This is under review in Mobihawk 19. Suppose each base station records timestamps of outgoing calls, and we query how many calls are made at these two base stations between 9 and 10 am. Even anonymized call record data can leak user identity. For example, calls at night are generally made from home. So here we protect location and time of a call. To publish events in a delay tolerant fashion, we perturb timings by Laplace distribution. Like these real events here are perturbed to these red timings. We perturb location by a random walk on the network. Like this event originated here is published as if it is originated here. To support real-time interactive sensing, we add fake events following Poisson distribution with intensity dependent on privacy parameters, like these blue fake events here. We trivially extend this framework to spatiotemporal dimension. All these mechanisms achieve epsilon delta differential privacy. They preserve better utility for range queries than existing techniques. These methods are also simple and computationally efficient. Now let us discuss a couple of future research ideas. In a point cloud dataset, we want to cluster the data points inside a query range. This is useful in understanding spatiotemporal signals like air pollution, traffic, temperature, etc. by sampling. The idea is to preprocess the samples for efficient clustering at any arbitrary range. Our next problem is to select the shortest archived trajectory for a given queried source and destination. This is important for route planning for self-driving vehicles. The idea is to search in a subset of trajectories called core set, which reduces the search space. For example, here we can skip the middle trajectory from the core set. To summarize, periodicity can be accurately tracked in noisy streams. Euclidean learnings can make mobility analysis accurate, simple, and efficient. Privacy-preserving algorithms can provide reasonable accuracy for spatiotemporal data analysis. Mobility analysis, spatiotemporal signal estimation, and privacy-preserving algorithms are interesting, and they have important applications in real life. Thank you.